Okay, here's the second video for the handout from this week, and this is connecting to what's called permutations and combinations. And then again, we'll follow up in class somewhat with this. So definitely you want to look at this before you come to class. So this is the third page on the handout, the set of the handouts that you got from this Monday. So at the top of the third page, it should say the title should be there, choosing a small set from a larger set of things. I think it might have got copied wrong on one of the sets. But it says how many ways. So again, that's the idea about a counting principle. How many ways can you do something? How many total outcomes are there? And again, looking at the handout, I don't have to read the whole thing to you, but it says you have a game that has 52 tiles, 2 for each letter of the alphabet. So that's uppercase and lowercase. Like I said earlier, that would make 52 total possible things if you had upper and lowercase letters, since we have 26 letters in our alphabet. And it says how many combinations of selecting 5 tiles are possible. So this is a little different question from the one previously, although very similar again to, like selecting the ice cream thing we did in class, selecting 2 ice cream flavors, I guess you could say, out of the 8. Remember there were 8, I believe, ice cream flavors, and we selected 2. And we looked at how you could have students fill in either by actually coloring or by writing on that ice cream handout that I gave you, how many possible things are there. So this is very similar to that idea. So if you remember back to that, some people said, well, if you don't repeat the ice cream flavor, remember we ended up with 8 times 7, which was 56 possible different ice cream with 2 scoops on them. So this is related to that idea. Okay, so this says draw 5 tiles from a set of 52 tiles. So basically you have 52 tiles. So imagine again that you have these in this set. So like you have an A, and an A, and then a B, and a B, and so on, right? All of the letters, upper and lower case, dot, 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 dot. So you have 52 in there. So again, imagine if I'm pulling them out and it says that you draw 5 tiles. So I guess this is kind of like playing Scrabble. You draw 5 tiles. So imagine I'm going to pull out, 5 tiles. And so some of them might be uppercase, some of them might be lowercase, whatever. I could get an A, then maybe I get a D, lowercase, then maybe I get a S, maybe I get a T, and then maybe I get a W, something like that. Whatever. You get 5 out. And it says, the thing that it says is do not replace. Because basically you're going to keep these tiles in this game. You're not going to replace them back in there. So a lot of times you'll see this called without replacement in probability language or terminology, without replacement. Okay, so again, sometimes people use this kind of slot. In this case, they use a box method to say, here's the 5 tiles. 1, 2, 3, 4, 5. And we want to know how many tiles are available to choose from when selecting the first tile. Right here, well, we know there's 52, right? Because that's how many we have in the whole set. And then how many tiles are available to select from each of the next 4 tiles. And again, this is trying to get you to think about this step by step. Well, if I've already pulled out one, and remember I'm not putting it back because I'm keeping this first tile, well now there's only 51 left in the set, wherever that is. And then I keep that one, so now there's only 50 left for the third tile. And then there's only 49 left for the fourth tile, and 48 left for the fifth tile. Okay, so again, this is the fundamental counting principle. We're finding out what's the total number of possibilities for this situation. And this is also related to what's called permutations. Excuse me. Okay, so if we want to know the total number, oops, of possible combinations of 5 tiles out of 52. We multiply this together, and that's how we get our total. And this actually comes out to oops. Okay, so that's 311,875,200. And one of the things I like to point out here is you can connect this to lotteries. Think about when you have possible either 5-digit or 3-digit or however many digits or whatever it is for a lottery. That's how you end up with so many different combinations depending on what the lottery is set up as. So in this case, it's letters, and there's a lot of letters to choose from for each slot. And so you end up with 311 million different possible combinations. So you can see how that number gets very high very fast. Okay, so we're going to connect this to what's called permutations, just so you can see later. This is like saying, this is our R in our formula that we're going to look at later, in permutations and combinations. And this is our N, our total number of things, whatever the things are. That's just something to think about for later. Next two questions here, or the next two problems here, I called this one the American Idol problem. I just tried to make up something that would be somewhat connected. And use these to kind of show you again what's the difference between what we call permutations and combinations. We've kind of already talked about it in a way when we did the the ice cream cone problem. Remember that in class when you did that, we said that if you didn't care about the order of the ice cream cones, you got a different answer than if you did care about the order of the ice cream cones, meaning in terms of the scoops. So that's related to basically this idea of permutations and combinations. Okay, so on the handout here, the American Idol contestant problem, it says you have 4 final contestants are to perform on one night. And then it says the judges decide to randomly choose the order of their performance. In how many different ways can we order the 4 contestants? So what I wanted to do in class, and maybe we'll have time to do this, is use the Unifix cubes to model this scenario. So, basically we have 4 different contestants. 1, 2, 3, 4. Contestant 1, contestant 2, contestant 3, contestant 4. And the question I had here too is why might it make sense that the various orders make a difference in this scenario? And the idea here is that assuming when people perform, it might make a difference if they perform first as opposed to performing last. And so the order can make a difference. So if this is randomly chosen, then you can figure out, well, how many different possible ways are there to order these 4 different people. So if we were going to use the Unifix cubes, we basically would choose 4 colors. So I'm going to try to just show you a little bit. I can't do the whole thing here. So let's say we had a red, a blue, a green, and let me find one more. Let's say yellow for the Unifix cubes. Okay, so what you could do with kids especially is they could start building these different orders. So for example, they could have a red, and then attach that to a blue, and then attach that to a green, and then attach that to a yellow. That would be one order. And again, this is like the ice cream cone problem that you did. And then again, keep doing that, and we could reorder these, right? So then I could have the yellow, the red, and then the green, and then the blue, and the yellow, and so on. And with the Unifix cubes, they could actually try to compare all the different arrangements, starting with, this case would be red, blue, green, yellow. So red, blue, green, yellow. And then you could order those in different ways. One of the things I posted on Canvas, one of the links, the video links, is talking about this similar type of thing of arranging and looking at the different combinations that you can get. So you might want to look at that also to help you see. You could make a tree diagram here. Again, you could start with red, blue, green, yellow, and then for the second slot you'd have whoops, you wouldn't have red, red, because the person can't go first and second. So you just have blue, green, yellow, and then for this one, you'd have red, yellow, green, and then for this one, you'd have red, blue, green, and for yellow, I always run out of space. Oh, I'm sorry. Did I do something wrong? Not red, blue, green. Oops. Red, blue, yellow. And then for yellow, I'd have red, blue, green. And then from here, think about this. If it was red and blue, so red and blue, then the only two things left now are green and yellow. And that would be how you would do all your, you could write all your tree diagram. I'm not going to write the whole thing, but you can see whoops, keep writing the wrong thing there. And yellow would be blue and green. Okay, so you can kind of see you could do this. You'd have to keep figuring out from all of these how many there are. Okay, so you could actually draw this all out. The other way to think about it is you could make a kind of like an organized list. You could go red, blue, green, yellow, and then you could say red, blue, yellow, green, and then maybe red, yellow, blue, green, and then red, yellow, green. Oops, sorry about that. Red, yellow, green, blue, and then red, green, blue, yellow, red, green, yellow, blue, and then I could start with blue as the first, or whatever, and I could keep going, right? Dot, 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 dot. So there's different ways you could do this. We could even do like we did with the dice. We could draw a chart to help us. Red, blue, green, yellow, and then up here, red, blue, green, yellow. But remember, you can't really get red, red, because I guess that doesn't really quite work in the same way. You'd have to make a chart a little differently, because you have to have 4 orders, not just 2 orders. So I guess that won't work in the same exact way. So maybe that would be like, nah, that's not going to work. So you may find some other way to diagram. You can figure that out, some different ways you can do this. But the main idea here is to figure out how many different ways we can order the 4 contestants. And so this basically goes back again to what we did with the fundamental counting principle. There's 4 possible ways to get the first person, that's this. And then because they can't repeat because we're ordering them, you can't perform first and perform second. There's only 3 names left for the second slot, and then there's 2 names left, and there's 1 name left. And, this is a problem that you can vary this scenario, but I think most kids would actually get this, because you just think about if they put the 4 names randomly in a hat or a bag or whatever, a box, whatever it is, you're going to pull somebody's name out of 4, and then that person's already on the list. So that's why we only have 3 left for the second choice, and then 2 left, and then 1 left. I think that's pretty clear. So by the fundamental counting principle, we know there's going to be 4 times 3 times 2 times 1, 24 possible arrangements, or orders of performance in this case. And so again, you don't have to necessarily list them all unless you wanted to do that for some reason. But in this case, if we want to just know how many possible there are, there's 24. Okay, so what we're going to do, and we'll do this more in class, this is going to relate to this permutation formula. This is called a permutation. When you have a set of things that you're ordering, that's called a permutation of things. And so this is basically would look like this, and like I said, we'll follow this up in class. This would be called like 4 permutation 4, because it basically means we have 4 things and we want to order all 4 of them. The way the formula looks, it would look like this. It's called 4 factorial, and we'll talk more about that in class. And then 4 minus 4 factorial. Okay? So again, for right now, don't worry so much about the formula. We'll follow that up in class. But I would say if you get a chance, watch the video that I posted where this guy talks about factorial, and you'll be able to follow it up with this and connect to this. I think that will help you up and see. Okay, so one thing that we're looking at is permutations in terms of ordering. So the second part says if you just have winner and runner up for this same problem. Okay, so it says the show ran at a time for voting and just has to determine all the possible ways for randomly choosing a winner and a runner-up. How many possibilities are there? So again, in this case, it says from the 4 final. So again, we have the 4 final people in here. So let's just use the same thing: red, blue, yellow, green. In this case, it just says we're going to randomly choose 2 of them. We're going to choose 2. Okay? And so it doesn't necessarily say that there is an order, right? But it says we're going to have a winner and a runner-up. So there is an order implied, and that's how you would know eventually, if you're using a formula, you would know whether you're going to use permutations or combinations. You can easily do this without a formula because we've already done this many times already. We did it in class with the ice cream cone problem. We've just done lots of problems here on these little videos that I've given you. So if you're going to choose 2, we just basically use those slots like we did before. So how many, let's say the runner-up gets chosen first, randomly. Whoops. How many possible names are there? There's 4. And then the winner gets chosen, let's say, second. And how many possible are there? There's 3. So we know there's 12 possible combinations of winner and runner-up, or possible outcomes, let's say. Okay? But because there is an order here, for example, if you're either going to be the winner if you get chosen first or second. So there is an order here. And so that's, again, how you would know by formula. If you're going to use a formula, you would use a permutation formula. So again, we'll talk about this more in class, but the formula would look like this. It would be 4 permutation 2. This is our total number, and this is how many we're choosing, which is R, or there's different formulas. I'm using N and R. You might see it written in a different way with different variables. And if you do this formula, you're going to get this, which we already know because we've done it multiple times, that the answer is going to be 12. This one would be a little easier to write it out because there's only 12 possible outcomes. And again, if you connect this to what we did with the choosing two flavors of ice cream, if you take the 24 from the previous problem and take out all the repeats, remember we did that in class, then you can look at, what happens if the order doesn't matter. So what if choosing a pair that's just two contestants and the order doesn't matter? If you take out all the repeats, you actually end up with, if you're choosing two contestants out of 4, you only end up with 6 pairs if you take out all the repeats. So 4 permutation 2 is 12, but 4 combination 2 is actually just going to be 6. And again, we'll follow this up with the formula in class, but I just want you to make sure you can see the difference in why something is in order versus not in order. Okay, so the video too long on this is the pizza toppings, and you see this type of problem many times in different variations. It's kind of the same thing again as the choosing the ice cream toppings or the ice cream flavors, same kind of thing. So this says you have a school party, the kids are making pizzas, there's 4 toppings, and you want to know how many 2 topping pizzas. So again, this is basically like what we talked about before with the ice cream. There's 4 toppings, so it says what? Pepperoni, onions, mushroom, sausage. How many 2 topping pizzas are there? So again, the idea is we're choosing 2 out of 4. So again, it's like the ice cream. We chose 2 flavors out of 8 with the ice cream cones. This is not the same as the winner and runner-up because it doesn't matter which order we choose this. If you were getting chosen as the contestant and they said if you get chosen second, you're the winner, then you probably want to get chosen second if you want to be the winner. In this case, we're just choosing 2. So if I do pepperoni and sausage, that's the same thing basically as sausage and pepperoni. They're not really any different, right? There's not, if you say pepperoni first or sausage first, you still get both pepperoni and sausage on your pizza. And again, we're assuming we're not talking about all the different things you could do, like half pepperoni, half sausage. We're just saying if you had 2 toppings and you chose, if you had 4 toppings and you chose 2. Okay, so this is kind of again the same idea. These would not get counted twice, just like with the ice cream cone toppings. If we didn't care about the order, then those would not get counted twice. So basically the idea is this is kind of no order in a sense. And so again, if we were going to use a formula, then we would use the combination formula. You can solve this without the combination formula again because we've done it multiple times, like I said. We could just draw out all the possibilities, or figure them out. But if we were using the formula, this would be again 4 combination 2. And then we would calculate that using the combination formula. And it would come out to 6 possible different 2 topping pizzas. And again, this is kind of imagines that we're not counting pepperoni and pepperoni as a pizza. Okay, so what I want you to do is just hopefully view this, come with any questions, and then we will connect this to the formula in class. Okay?